So I'd like to start first by thanking the organizers for inviting me to this beautiful place and giving me the opportunity to tell you about some of the work that we've been doing to explore the use of nitrogen vacancy center magnetometers in order to learn about novel properties of materials. Now, as I'm sure you know, nitrogen vacancy centers are very sensitive magnetic field sensors, and the challenge in applying these sensors to condensed matter systems is that very often the physics that we're interested in is not easily connected to the magnetic field that the sensor detects. And so the goal in this talk would really be to go through a few examples of interesting phenomenon that exist in solids and to see how these phenomenon are linked to the measurements or the quantity that a nitrogen vacancy spin qubit measures. So specifically, I'll address several phenomena that are listed here. We'll be interested in learning about magnetization, static magnetization. And as you'll see, an NV center does not measure directly magnetization, measures magnetic field that's generated by that magnetization, and that puts some very significant constraints on what we can actually learn by doing a magnetic field measurement on the magnetization properties of a desired material. A lot of these materials are materials of interest, such as magnetic materials, but it could be also frustrated magnets, have spin excitations. These could be spin waves in the form of magnons, but these could also be other spin excitations. For example, you have monopole-like excitations in spin ice materials. You have interesting spin excitations in spin liquids. So we're interested to see, is there a way that we can learn about the spin excitations in these materials? And specifically, we'll be looking at how could we detect spin chemical potentials in materials where the number of spin excitations is more or less conserved. Once we have some way of monitoring spin excitations, you might also ask, well, what about transport of these excitations? We can induce some chemical potential difference of spins and monitor spin currents. How could we detect, or what would be the signatures of spin transport, spin propagation in some materials? And lastly, if time permits, we'll see, I'll talk about signatures of interesting electron flow. It turns out that there are certain materials where the interaction between electrons leads to viscosity, and the kind of electron flow that one finds in these materials resembles very much those that you find of gases or liquids flowing through pipes. And here again, I'll talk about what are the manifestations of this kind of hydrodynamic flow in the context of NV magnetometry, specifically both current imaging and also just signatures of the hydrodynamic regime itself through noise. Now, beyond the interest to try and extract information from interesting materials using NV centers, one can also think of the reverse, where one is interested in using some of the interesting magnetic excitations like magnons to do something useful in the context of spin quantum bits. For example, can one use magnons or magnon resonators in order to entangle two neighboring spins? This is really an open problem right now. The challenge of entangling atomic spins over large distances is something that is really extremely challenging, and maybe magnonic resonators could be a way that one could go about doing that. Another interesting application is to use magnetic materials as amplifiers or enhancers for magnetic sensing. So imagine there is some magnetic field that we'd like to detect using the spin sensor. One can imagine in a particular narrow range of frequencies, if we interface our sensor with a well-known magnetic resonator, one can imagine gaining sensitivity and amplifying the signal, thereby having better sensitivity in a narrow bandwidth, but with higher sensitivity. So I'm not going to talk about these last two examples. I'm really going to focus on the extraction of information from materials using NV centers. And so let me give just a very brief two-slide introduction to nitrogen vacancy centers. I'm sure you all heard talks about these defects, and so I don't really need to go too much into detail. So the underlying ground state manifold of a nitrogen vacancy center is a spin triplet. It has the absolute ground state is an ms equals 0 state. It has two excited states with angular momentum plus and minus 1, and these depend on magnetic field linearly with a G factor of 2. One of the key features of the nitrogen vacancy center is that it's atomic in scale, and so it provides information on magnetic fields on an atomic scale if you can bring it close enough to the surface. And so some of the efforts that have gone into this field is to really develop tools and techniques that allow you to bring one of these defects close enough to the center. And for certain applications, I'll talk about paramagnetic spins in the introduction, but for most of the kind of novel materials applications, what determines the wavelength or spatial sensitivity is therefore not given by the atomic size of the defect, but in fact, how close can you bring it to a particular system of interest. It's a relatively non-invasive probe in the sense that one could initialize it and detect its spin state optically, so we don't need any electrical connections to the system. And as long as light does not interfere with the kind of physics we're interested in, then it works really well. And one can also, especially for magnetic phenomenon, one can easily screen out or reflect the light if it is interfering with the experiments, such that we're only picking up the magnetic signal without having to worry about the excitation. As a magnetometer, there are several different modalities that one has developed in this field. The simplest one is to look at absorption. So if we are at a particular magnetic field and we scan some microwave frequency and we see at what frequency is there an absorption, then that frequency will match one of these transitions from the ground state to one of these excited states. And hence we can determine magnetic field very precisely simply by looking at what frequency is their absorption. The absorption will be precise at the magnetic field, and hence this technique is very useful when one is looking at very low frequency magnetic fields. If one is interested in some intermediate fluctuating magnetic fields in the range of megahertz or hundreds of megahertz, then it turns out that there are AC type techniques that provide even enhanced sensitivity, whereas the DC kind of sensitivities that we can get at low frequencies in the range of microtesla for 1 second of integration, at these kind of intermediate frequencies, we can get down to the few nanotesla sensitivities, and in fact, you can improve this with ensembles. There are many, many ways of improving things in this field. This is just the more or less state-of-the-art, or typical, I wouldn't even say state-of-the-art sensitivities if one works at some intermediate frequencies, a few nanotesla per root hertz. And finally, if one is interested in higher frequencies on the scale of the transition frequencies of the NVs, then one is looking at relaxation. So as I mentioned, distance is really crucial. And so over the years, we've developed a tool set that allows us to bring NV centers really close to the surface. Here you can see one of our earlier versions of a scan probe, which is made of a monolithic piece of diamond. You see the fabrication process here, where one starts with a sheet of diamond that's about it's cut to be about 50 microns thick. We then thin it down to a membrane of about 3 or 4 microns. We do electron beam lithography on that membrane to produce these pillars, and the pillars already have implanted nitrogens in them, such that statistically there would be 1 nitrogen vacancy center per tip here. And then we can fabricate either single tips, single pillars on a cantilever, or multiple. We will then characterize, identify which one of these NV centers is good, which one of these pillars has 1, 2, 3, or 0. And we would then mount these cantilevers directly onto a quartz rod. The pillar here serves 2 functions. One is as a waveguide to collect the light, and of course the other is to be the lowest point of this structure so that we can approach the surface very effectively. And typical distances of these single defects from the surface is on the order of 10 nanometers, which is easily achievable. If one wants to bring the defect closer to the surface, then usually one loses sensitivity because the surface has a lot of fluctuating spins, and so there's going to be a compromise So if spatial resolution, let's say, is more important than sensitivity, then you definitely want to bring your sensor to be a few nanometers, 1 or 2 or 3 nanometers from the surface. As way of introduction, let me just mention a few things that we've done using paramagnetic spins. So paramagnetic spins are, of course, spins that are not interacting with one another, and hence you can, in fact, control them remotely by shining RF radiation. So on paramagnetic spins, we've demonstrated that we could image the magnetic field of individual electron spins in real space. Here you can see one rough image of that. We've also shown that by introducing magnetic field gradients, one could actually do full three-dimensional magnetic resonance imaging, same as you have in a magnetic resonance imaging at a hospital, only here our spatial resolution is a fraction of a nanometer, and the magnetic field gradients that we're using are about 5 orders of magnitude larger than what you'd find in a commercial instrument. And hence, these techniques are obviously limited to nanometer scale and not a body scale, but nonetheless, really phenomenal spatial resolution in full reconstruction without a model. So there are a lot of advantages of using NV center magnetometers in this context of paramagnetic spins, provides tremendous enhancement of spatial resolution. There are many different ways of approaching the surface. I've already talked about the scanning version. There's another version in which you have fixed NVs on the surface and you actually scan a sample. So you can imagine mounting your sample on a tip that you can scan around and then image with a static nitrogen vacancy centers. These techniques are more demanding, obviously, because they are scanned. The simplest one that you can imagine to get real nice spatial resolution at one particular point is to put a material of interest directly on top of the diamond that will have then, let's say, one NV center is a few nanometer from the surface. This doesn't have the scanning capability, but is a much, much simpler kind of experiment where you don't have to worry about crashing your tip and making these tips. But not always can you actually bring a material of interest to the surface of diamond. We tried this, for example, when we were starting out working with YIG, to actually grow YIG directly on diamond thin films, and it's really a very difficult process, and the quality of the films that you get are very far from the ones that you'd get on GGG. So then we developed a different approach, and this one is to basically create nanobeams within diamond using angle etching. And in these beams, we have a few of these NV centers. We can then pick these nanobeams up using a metallic tip and place them on top of a surface. And here you can see a YIG film that has been etched and one of these nanobeams that is now sitting directly onto this YIG layer. And the nice thing about these prisms is that they very much serve the same role as the waveguide. They really allow a lot of the light to come out. And so the sensitivity of the probe is very high using these kind of structures. All right, so now past this general introduction, I'd like to start talking a little bit about the imaging of magnetization, in particular skyrmions. So just 1 or 2 slides on skyrmions. So skyrmions are basically a result of the competition between exchange interaction and the Jaluzinski-Moriya interaction, which is a result of spin orbit that you have in some materials. And this competition, if you think about this in mean field, gives rise to a chiral order, where the spins favor the lowest energy configuration of this kind of Hamiltonian would be to have a particular angle between spins given by the ratio of d to the exchange, and this gives you a chiral magnet. When you apply magnetic field, you favor one direction in space. This collapses these structures to skyrmions. And it turns out that there are actually different ways of generating this spin-orbit interaction. One is just bulk inversion asymmetry. And you have skyrmions that appear, these are skyrmion tubes that appear in some of these bulk materials. But another one, which is really interesting from an application standpoint, is to generate the spin-orbit interaction in a different material that's not even necessarily magnetic. So here you can have a bilayer of a magnetic material where the spins want to align one parallel to the other, only exchange, and a spin-orbit interaction where there's no magnetism whatsoever. And this hybrid actually favors formation of skyrmions in thin films a few nanometers thick. And this is actually what we will be imaging. The underlying textures of skyrmions are topological, namely, if you were to wrap the spin texture on a sphere, what you find is that every angle on the sphere gets hit either precisely once or precisely twice or three times, namely the coverage of the sphere using the magnetic texture is really an integer. And that corresponds to the topological charge. That's also what gives them their stability. You can't really relax a skyrmion to no skyrmion or to a skyrmion with a charge of 2 because it requires a discontinuous deformation of the spin structure. And important for this talk will be the fact that in a magnetic texture where you don't have discontinuities in the spin arrangement, it turns out you can show mathematically that energetically it is favorable to the system will always have an integer charge. This coverage will be integer, and you will not have any fractional coverages. So if you deduce some magnetization texture in your system and you map it onto this sphere and you find only partial coverage, you know that that's not a correct pattern of magnetization that is in the system. The competition between surface and bulk inversion asymmetry can give a rise to different types of skyrmions. You see here the projection of the spin onto the plane is along the tangential direction, whereas here it's along the radial direction. These are called block, these are called nail, and so we're going to be looking to see and conclude what kind of topological order exists in the materials that we have imaged. For this particular experiment, we are using this inverted geometry where we have fabricated these magnetic layers and done e-beam lithography directly on a quartz tip. You can see here a 50 micron quartz tip where we have a few of these 2 micron disks made of multi-layers of platinum cobalt. So if you zoom in onto one of these and you're now looking at the fluorescence that the NV center is emitting, it turns out that fluorescence is not a direct measure of magnetic field, but it gives you already information about magnetic field, and in particular magnetic fields that are acting perpendicular to the axis of the NV center. It's a very fast way of extracting information about the system, but it's not qualitative. So what you can see here is starting from 0 magnetic field in one of these disks, you have some magnetic domains, but as you crank the magnetic field, eventually a ball appears, and this is what we think is a skyrmion. So this is very qualitative. We only are picking up the off-axis magnetic field, and we don't know their magnitude. We certainly don't know what the magnetic texture that this kind of image corresponds to. So now we can go ahead and do a more quantitative analysis. So if you remember, the NV center has these 2 transitions from the ground state to the ms equals -1 and to the +1. And so we can record, as we're moving our tip around, we can record what the frequency of the lower transition is and the frequency of the upper transition. And in fact, it turns out that you need both of these transitions in order to reconstruct the magnetic field along the axis of the NV, which is shown here. This is in fact linearly dependent, so the signal to noise here is linearly dependent on magnetic field, but you can also use these 2 frequencies to construct an image of the magnetic field perpendicular to the NV axis. Now this comes in only quadratically because you have to compete with the 0 field splitting that the NV center has, and so this kind of off-axis magnetic field is noisy. And you'll see in fact this measurement is redundant, and this is part of the learning process that we have undergone in this field. So now we have quantitative magnetic field measurements. This scale is in Gauss, both along and perpendicular to the NV axis. And now we can ask, okay, how does that relate to a magnetization pattern? So let's go through this slowly. So imagine I have a magnetization that is uniform, completely all spins parallel. It turns out that the magnetic field that this pattern is generating is just 0. And the reason is that each one of these spins you can think of as a small current loop. And when you put a lot of current loops together, all the currents in the bulk cancel. And so if you're very far away from the boundaries and you're very close to the surface, you're not going to be picking up any signal. What about an antiferromagnet? So an antiferromagnet will generate magnetic fields locally. The problem, however, here is that the scale over which these magnetic fields are fluctuating is an atomic scale, and as long as this distance d is greater than this length scale, we're going to be just suppressing our sensitivity to these very short wavelengths exponentially. So both q equals 0, or k equals 0, and very large k, we're not going to be sensitive to. It's not hard to convince oneself that the sensitivity or the signal that we'll pick is something that has to go between 0 and 0 for small k and large k and has a peak, and the peak actually appears at a k vector of around 1 over the distance to our sensor. And that's why I was saying that if we can get our tip closer, or the NV center closer to the surface, we should be able to probe shorter and shorter wavelengths inside this material. And you'll see a very nice example of this in a little bit. Now, one can, of course, do this thing very systematically. So you can start with each spin, calculate what the magnetic field is generating at the point of the sensor. You can integrate all these magnetic fields, which leads to a convolution. And if you go back to Fourier space, and k is that wave vector of magnetization that is changing in the space, in the plane, it's a very simple product between the magnetization pattern and the magnetic field. So in principle, the only thing we need to know to do, if we know what the magnetic field is for every k, and this is both a magnitude and a phase, so we need to image magnetic fields in this entire plane and take their Fourier transform, and so we'll have B of k. In principle, if we could just divide by this dipole tensor, we'll get the magnetization. But there is a problem. So first, let me just point out that when you do this kind of systematic analysis, you get very nicely this function, this quality or form factor, which is k times e to the minus dk, that exactly describes this filter function here, indicating what kind of q vectors are we sensitive to. The complexity is that this dipolar matrix is singular. And it's singular because each one of its rows is directly related to the other row. And so this has, a good news and bad news to it. The good news is that, we can basically just measure one component of magnetic field. We don't need to measure 3. And we can deduce all others. That's why I was mentioning before that measuring the perpendicular component of magnetic field is redundant. You'll see that very clearly. So that's an advantage. In effect, when you want to measure magnetization of thin films, measuring one component of magnetic field tells you about the full vector field in space, not in one plane, but anywhere in space. But the challenge, of course, is that now we can't reconstruct the magnetization because this matrix is singular, and in fact, there are infinite sets of magnetizations that will produce precisely the same magnetic field pattern. So just to demonstrate this kind of effect that we can measure one component of magnetic field and extract all others, so here is the magnetic field that we measure, let's say, along the NV axis. And we now construct magnetic field based on that dipolar matrix along z, x, and y. And now we can take the magnetic fields from these 3 components and compute what the magnetic field is along the axis perpendicular to the NV. And we can compare it to our measurement. So that's our measurement that I was mentioning is noisy because you're only sensitive to the magnetic field quadratically. And this is this reconstructed magnetic field from the one that is linearly sensitive from the one along the NV axis. And you see that we get the same information, only much higher quality. So this is a true property of magnetization. And the challenge in determining magnetization for magnetic field is the fact that you can't reconstruct magnetization directly. You, in fact, need more physics in order to work this problem back. So this is the problem. We're measuring magnetic field, and we need to determine the magnetization, but we really lack information in this process. Just to give you an example, remember this kind of filter function that has k times e to the minus dk. This prefactor k should remind you in Fourier space, k means derivative. So in fact, the NV center is sensitive to gradients of magnetization, not magnetizations themselves. So anytime you have something that is, in fact, divergenceless, one can show that that does not add any contribution to magnetic field. So this already gives you a sense of the fact that there are infinite solutions that would generate exactly the same magnetic field. So nonetheless, we're really interested in finding out what is the texture associated with the skyrmions that we were observing. And so one could basically search for different magnetization patterns. And these are magnetization patterns that correspond to the block type of skyrmions, where the projection of the spin is tangential, more or less. And you can see that this specific magnetization pattern produces magnetic fields that are as accurate as we would desire to the measured data. And you can see the line cuts here going through the data, very, very strong and good agreement. But when we map out this texture onto the block sphere to see what is the topological charge of this texture, you see that it's not integer. It's about a half. So we know this is not a physical solution to this texture. If we, however, fit the other type of skyrmion, the one that is the nail, spins projected along the radial direction, this one gives us full unit coverage, which then is very consistent. And the story is more complicated than that, but at this point I just wanted to demonstrate the kind of complexity and challenges associated with extracting magnetization by measuring magnetic field. All right, so now I'd like to talk about the second topic here, and that is looking at magnetic excitations and trying to see how would we probe, let's say, a spin chemical potential. We're interested in magnetic excitation already I mentioned, for a variety of reasons. There could be superfluidity associated with these magnetic excitations. There could be interesting excitations in spin liquids, dynamics of various textures. The way you should intuitively think that we're actually exploring these excitations is by realizing that the time-dependent magnetic field in the system would lead to both decoherence and relaxation of the NV center. So we have a lot of knobs that we could use in order to extract what are these fluctuating fields are. So in order to determine a spin chemical potential, the spin chemical potential is directly related to the number of magnons. So the number of magnons, if these are just thermal magnons, obviously will generate noise. And if this noise is precisely at the frequency of the NV center, it would lead to relaxation. So the scheme that we have selected is one where we are trying to look at the rate of decay of our NV center due to the noise generated by the magnons. And of course, this is going to be a complicated function. It's going to depend on the density of states. It's going to depend on this Bose factor that has magnons in it, but also depends on temperature. So it depends on a lot of parameters that we don't necessarily have a handle on. So it would be really nice to find a method in which we don't need to know all these extra properties of the system. And what it turns out is that if you do a comparative measurement, you compare two different types of measurement. One is you look at the relaxation rate of your NV center at the same location above this magnet, but in the absence of pumping, without adding more magnons. So just due to the thermal magnons that are there, you would get one rate. And that rate I call the rate in equilibrium. And if you now compare that to a situation where you take the magnet out of equilibrium, so namely you've pumped magnons and you've raised the chemical potential, so it's no longer zero, you get a new rate, which is rate with drive. And it's not hard to show that the chemical potential of the system is given by the ratio of these rates, 1 minus this ratio times the frequency of the electron spin resonance. So by measuring these two quantities, there are no more unknowns. You're directly going to extract the chemical potential, and you could see how this chemical potential depends on how strong you drive the system out of equilibrium. And we've explored two different ways of driving the system out of equilibrium. One is to drive directly the ferromagnetic resonance and see if we can enhance the number of magnons that way. And the other is just through spin injection, which will also pump spin magnons into the system and raise its chemical potential. All right, so here's the first measurement. This is the rate in equilibrium. So we're basically looking at the relaxation rate. Essentially, we're preparing our NV center at one of these excited states, and we're looking at how long it takes it to relax. And you can see these are the two transitions of the NV center in a plot of frequency versus magnetic field. The bottom line here is the Cattell mode, the ferromagnetic resonance. And of course, at any given temperature, for any given field, this kind of colored shading describes roughly the occupation of magnons in the system. And so what you see is that this transition from 0 to -1 is actually starting at a place where there are relatively few magnons at low field, but as we increase magnetic field, this line is diving lower and lower into the magnon band, and therefore you see more and more magnons. And in fact, if we look at the relaxation rate, we see precisely that. We see that the relaxation rate starts low and then increases until it gets to the ferromagnetic resonance, where there it suddenly drops. And the reason it drops is that once we cross the ferromagnetic resonance, the magnet has no more modes, fluctuations, that will lead to relaxation of the NV center. So we see a sharp decay. In contrast, you could look at the other transition from 0 to +1. It starts relatively low. In fact, they should start at the same point, but there are other geometric factors and considerations that go into this magnitude. And then as you go to higher and higher fields, you're now removing yourself from the magnon band, and therefore the relaxation rate is more or less constant and independent of magnetic field. So this is one measurement that we need to do. The second measurement that we need to do, and the contrast here is not so great, but hopefully you can see a little bit this ferromagnetic resonance. So what we're doing is we're driving the magnet at its ferromagnetic resonance now. And so what happens is that the magnet is driven, and yet we see relaxation of the NV center. Now, the NV center is not sensitive to this ferromagnetic resonance frequency. It's sensitive to a frequency that's much higher, and yet we see relaxation. And the reason is that these modes, these magnons that we pumped in by driving the system at the FMR, relax, and they populate magnons at higher frequencies, including the frequency consisting of the ESR, and therefore we see relaxation. So we can now monitor, as a function of magnetic field, what happens to this, to the lifetime of the NV, the relaxation rate, and construct a plot of what we deduce is this chemical potential from this simple equation. And this is what this color map is showing here. So this color map is showing on the vertical axis chemical potential, and on one horizontal axis is the drive power, how strongly are we pumping magnons into the system, and on the other axis, magnetic field. And what you can see is that indeed, as we're pumping magnons, we're driving the magnet, we see the chemical potential increase. So that's what we'd expect. But we also saw something that we initially didn't expect, and later we understood and took it to be very strong confirmation that we understand actually what we're doing, and that is that this chemical potential, or the extracted chemical potential, saturates. And note that it saturates precisely at the value of the ferromagnetic resonance. So we're pumping magnons into the system is increasing its chemical potential, but that chemical potential cannot exceed the bottom of the magnon band, because this is a boson system, and the system, if you pump it hard enough, will just populate the ground state with a larger and larger population. In principle, this could be a condensate. We don't have direct evidence that this is a condensate, but what we do know is that the chemical potential does get pinned to be at the bottom of this ferromagnetic, of this magnon band, and that gives us a real strong confirmation that this procedure, what we extract to be the chemical potential, is indeed the chemical potential in this system. Now, one interesting thing that was also unexpected is the fact that you see at low magnetic field, it actually requires a little bit of pumping in order to drive the chemical potential up. It's a very nonlinear process, and we don't fully understand the nonlinearity that we see here, but we do understand what happens at very low power. And if we just focus on this very low power regime, we see that the slope of the chemical potential with power is linear. the behavior is linear, and we can extract what the slope is. And these are the data points here, red and blue, is the slope, is the dependence of the chemical potential on power. And the purple line here is theoretical prediction by Yaroslav's group. And what you see is a very, very nice fit. And the explanation is that this is basically the thermomagnonic effect that allows you to relax the coherent magnons that you're pumping into thermal magnons. And the reason you have this kind of very strong magnetic field dependence, where there is very weak change in chemical potential at low fields and strong dependence in high fields, has to do with symmetry. In order to run these experiments, we need to align the external magnetic field parallel to the NV axis. The NV doesn't like magnetic fields not along its axis. And this magnetic field there, as we're ramping it up, what it's doing is pulling the magnetization out of the plane by a tiny bit. But it turns out that the conversion of these pumped magnons to thermal magnons is forbidden as long as the magnetization is in the plane. And only when you pull it out do you begin to get that pumping of the thermal occupation of magnons, and this is why you have this kind of very slow onset with magnetic field. All right, so this was a demonstration that using a nitrogen vacancy sensor, it's a magnetic field sensor, yet we can extract chemical potential. Now I'd like to talk a little bit about propagation of magnons, long distance propagation, and coherent control using these magnons to drive NV rotations. This is in fact a topic that has been studied over the past several years by several groups. Recently there have been some really nice experiments on long distance excitation or control of NV centers up to several millimeters away from where the source is. Really a nice indication that these magnons propagate extremely long distances and maintain their coherence within a narrow band, because that's what's needed in order to drive coherently nitrogen vacancy centers. So far, we focused, again, color is not great, but we focused on the ferromagnetic resonance, which you can barely see here. But now I'd like to focus on this bright feature here. This is when we drive the system precisely at the electron spin resonance, so we should expect a change in the occupation and therefore a relaxation or decay of the NV state from its prepared state when we're along this line. But what you should note is that this experiment is done when the NV is very far away from the source. So it's no longer directly sensitive to the magnetic field that we're driving. It's only picking up magnetic field that is present inside the magnet several tens of microns away from the drive. And so the question that first we wanted to ask ourselves is this kind of signal that the NV is seeing is coherent, or it's just thermal and it's just decay? And so indeed it's coherent. You can see very nice Rabi oscillations of this NV when you're on this line. So we know these are coherent oscillations. But it turns out that you can actually learn much more, in fact, even what the dispersion of magnons is by looking at this curve. So let's see how this works. So remember our filter function. We're not sensitive to k equals 0 magnons, and we have this kind of peak, and we're not sensitive to short wavelength magnons. So in fact, when we're walking along this line here of the electron spin resonance, when we start out exactly at the ferromagnetic resonance, note, the magnons that drive the nitrogen vacancy center are very low energy, long wavelength magnons. So the intensity here, precisely at the FMR, should be 0, because even if we have these k equals 0 magnons in the system, they're not going to produce any magnetic field, and the NV center will not pick it up. As we're moving along this line, the energy from the bottom of the band is changing, so we're basically changing the k, the momentum of the magnons that we're exploring. And so if we see a particular feature on this line, we can immediately extract, knowing its energy, and if we can say something about the momentum, then we can extract the dispersion. So if we look at this curve, note that this curve, we're now sitting 1 micron above the magnet. So 1 micron above the magnet means that we're not going to be picking up any magnon that has a wavelength shorter than 1 micron. So this cutoff here is going to be determined by this height, 1 micron. And this line shape here follows very nicely this kind of filter function that we've derived before. If we increase the height to 2 microns, you see that this thing shrinks. I'll just plot here where the FMR is. So you see, again, we start from the FMR, we peak, and then we go down. And this point is moving simply because the wave vector of the magnons that we're sensitive to now is only limited to 1/2 microns. And here it's 3 microns. And so by knowing that this wave vector here is precisely 1/d, and measuring its energy, we can reconstruct the dispersion, which is something that we're doing right now in greater detail beyond these 3 data points. So this is very nice. We can basically see the propagation of magnons over long distance and, in fact, use the height of the NV as a wave vector selector in order to extract full dispersion information. Okay, last topic that I'd like to cover is that of hydrodynamic electron flow. And hydrodynamics, as you very well know, has been used to describe quite a bit of different physical phenomena. Here you can see, for example, superfluid helium can be described in terms of hydrodynamic physics, where basically the use of hydrodynamics is a conservation law. It's based on some conservation laws that exist in the system. And in the case of superfluid helium, this conservation law has to do with spontaneous symmetry breaking. If you have a system that has a well-defined order parameter, if there is a spontaneous symmetry breaking, there is a random selection of that phase, and gradients of that phase correspond to superfluid currents. In fact, the field of spin superfluidity is basically was started out by this work here by Halpern and Hohenberg, where in fact they specifically say that they're deriving a mean field theory for magnets that is directly analogous to superfluid helium, and it indeed describes the properties of the system in terms of conservation laws based on spontaneous symmetry breaking. But I want to talk about a different kind of hydrodynamic regime, which is that you can find in the flow of gases or flow of liquids. Normally we think of let's say, an electron gas as a system that has a lot of momentum relaxation processes in it. We're thinking of non-interacting electrons, and these electrons scatter off impurities, they scatter off phonons. So overall, the momentum of the electron system is not conserved. Current is conserved, but each electron is losing its momentum on a very fast time scale. However, you can imagine a system where it's extremely clean and phonons are not playing an important role. In this particular case, the electrons will be strongly interacting. They will be scattering rapidly one off the other, but the average momentum of this electron gas or electron liquid is conserved. So in this case, again, there is a hydrodynamic description of this system where the conductivity will now depend on the viscosity. This kind of interaction between electrons will give rise to viscosity very much in the same way that you have viscous gases and viscous fluids. And a lot of what your intuitions tell you about how a viscous fluid should flow in a conductor, in a pipe, would follow for these kind of systems. In fact, a lot of in certain systems, one finds that the electron-electron scattering rate is as fast as possible if one wants to still use Fermi liquid theory. So Fermi liquid theory tells you that the lifetime of excitations cannot exceed 1 over the temperature, and in fact, in some systems, there have been experimental demonstrations that this electron-electron scattering rate is precisely given by h bar over kT. So this kind of maximum limit was also given the name of a Planckian limit for the reason that it's basically saturated by h bar over kT. There is a lot of work that is trying to explain some of the properties of high temperature superconductivity, and in particular, what's called a strange metal, namely the linear dependence of resistivity on temperature above Tc in terms of hydrodynamic properties. And there's a lot of complicated theory that people are deriving to produce this kind of Planckian limit in the case where the system is very strongly interacting. So it turns out, however, there are also rather simple systems that show this kind of behavior. And in fact, this revival of this field started out by experiments from Andre Geim in graphene that showed that this kind of hydrodynamic viscous flow can generate interesting turbulence inside the electronic system due to some unconventional current flow patterns. So in the context of what we're interested in, you can say, well, what are the manifestations of hydrodynamic flow in the context of measuring magnetic fields? So the simplest one would be just the looking or trying to see what is the effects of the current flow pattern. So in a Drude type flow where momentum is not conserved, so momentum relaxing processes are very rapid compared to momentum non-relaxing processes, one expects a uniform flow pattern. But if you have viscous flow and the boundaries are such that they scatter momentum, so you have some kind of diffuse boundary and you have strong interactions, it turns out that the profile of current flow is now universal and is given by a parabola. This is called Poiseuille flow, very well known from fluid mechanics. And in fact, if you have some momentum relaxing processes, then this you will have a boundary layer and then you'll have some flat top depending on the dimensions of the system. So one can define in principle a length scale that has to do with the ratio between the momentum relaxing and momentum conserving processes. And as long as the channel width is smaller than that length scale, you'll have a perfect parabola, this Poiseuille flow. And in the case where your channel width is greater than that dimension, you'll have a boundary layer, and then you'll have flat top eventually, but you will have a significant boundary layer that's dictated by the viscosity of the system. Now, as I mentioned, there have been some nice transport measurements by looking at voltage, current voltage dependencies, but these are rather indirectly, often depend on a particular model, so it's really nice to be able to extract this kind of current flow pattern. And of course, current generates magnetic field, and so we already have the methodology of extracting what the current flow pattern is, because currents in the plane you can easily envision as magnetization only pointing along the z-axis. So rather than having arbitrary direction in the plane, currents, I can map this problem into just a magnetization along the z direction for which there is only one pattern that matches a magnetic field pattern. So if you remember the beginning where I mentioned that measuring magnetic field does not give you precisely the magnetization, in the limit where the magnetization is only along z, then it's a unique solution, one-to-one correspondence between magnetic field and magnetization, and hence this is a precisely invertible problem. There is another interesting approach, and that takes advantage of looking at high frequency at noise, basically. So we know that conductivity is directly related to fluctuations through the fluctuation dissipation theorem, and this is current fluctuations. And so there's a nice theory paper from Eugene Demler and coworkers that show that depending on what kind of transport regime you are, the power spectrum of the noise will depend in a different manner on the height above which you're probing the system. So this axis is height, this is the power, basically the prefactor of the power spectrum, and you see that if you have hydrodynamic behavior, then this noise spectrum will be height independent, whereas for all the other kind of ballistic or diffusive flow, you will have height dependence for the noise. So this could be another very nice way of extracting information directly about the hydrodynamics. So let me just spend a few minutes giving you some results that we have recently acquired on graphene. Obviously, at very low temperature, graphene would be a non-hydrodynamic fluid because the rate of electron-electron interactions themselves depend on temperature. So you need to be at some intermediate temperature. And in fact, what you'll see is room temperature measurements of graphene showing very clear signatures of hydrodynamic flow in this system. Up to now, I've always discussed single NV imaging. Here you can see an array of NVs that are sitting in the diamond, and we have our graphene sheet sitting above it, so we can basically extract directly an image. Here you can see a current flow pattern extracted from this array of NVs. The channel of graphene is highlighted here in red. And you can see very nicely that we can integrate the current at any given cross-section here. So here it's integrated and we get 99 microamps. Here we're integrating it in a narrow channel, we're getting 100. So everything is consistent, current is conserved. We understand very well what the signatures are. And here's just a snapshot of how, when the NV centers are very close to the surface, the relationship between field and current. It's just a direct relationship. There is very little conversion that is needed. Now, of course, the downside of this kind of imaging technique is that your spatial resolution is given by the light, by the wavelength of light. So here's our measurement. These are the red dots. And this is what the uniform flow would have looked like with our resolution. So this is not great, but it already shows something that's fairly curved in the middle rather than flat. But nonetheless, we were very interested in trying to get much better spatial resolution. So here's a very recent measurement using our scanning approach, looking across the sample. Now you could see that a uniform flow is much sharper if that were the case, and we're getting something that's very, very curved, indicating that already at room temperature, this system is very much in the hydrodynamic regime. And this length scale that I mentioned before that's set by the viscosity we cannot put a upper bound, we can only put an upper bound, we know that this number is greater or equal to 300 nanometers. I don't know if this is, so I think it's a lower bound on this number. All right, so I think I'm done. So let me just conclude rapidly and say that NV centers are really a versatile tool. They really allow us to address new properties of materials that we were not able to do so before, and hopefully the kind of range of applications that one thinks about using these kind of very local sensors will be expanded as time goes by. Thanks.